In this video, we're going to talk about chords and a couple theorems related to finding lengths of chords and using lengths of chords to find different things. The numbers of the theorems in this video relate to a specific textbook that I've used in the past. If you use a different textbook, then the numbers might not match up. But if you're learning about chords, this should be helpful. So our first theorem says, in a circle, or in congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. So know that an arc is just part of a circle, and a minor arc is an arc that is less than 180 degrees. So PQ is a minor arc, QS is a minor arc, ST is a minor arc. And the chords are the straight line segments that connect the endpoints of the arc. So PQ is an arc, PQ is a chord when we cut straight across like that. ST also a chord cutting across the inside of the circle like that. So in this problem, they tell us that we're supposed to find x if PQ, that line segment, is congruent to ST, that line segment, so we just mark those as congruent, and the length of arc ST is 22, and the length of arc PQ is 5x minus 3. Now our theorem says that the arcs are congruent if the chords are congruent. They told us that the chords were congruent, so the arcs are congruent. So we just set up 5x minus 3 is equal to 22. Move the 3 over, 5x is equal to 25. Divide by 5, and x is 5. And that's all. One other thing to say about this first theorem here, well, first of all, so anytime you have congruent chords, you know that the arcs are congruent. And so here we were given congruent chords, so we set the arcs equal to each other and solved. Also, though, this says if and only if. And if and only if means that the theorem works both ways. So if I know that the chords are congruent, I know that the arcs are congruent. If I know that the arcs are congruent, I know that the chords are congruent. And so that's a very important thing to notice. So if you have a different problem where they tell you that the arcs are congruent, and you have to say something about the chords, you know that given that the arcs are congruent, the chords would also have to be congruent. So it works both ways, and that's what they mean when they say if and only if here. All right, now we have another theorem about chords and circles. So in this one it says if a diameter or a radius is perpendicular to a chord, then it bisects the chord and the arc that it creates. So in this example here we have this diameter and then this chord. And the chord FD creates arc FD. So here it says circle A, so we know that A is the center, which is how we know that this is a diameter because it goes through the center. It says that the radius is 10 centimeters, and it also says that AE is perpendicular to FD. So we know that this diameter is perpendicular to this chord. And then we also know that FD has a length of 16 centimeters. And now they ask us to find a couple other things here. So they say if the measure of arc FE, which notice we've got this little m here, so we're talking about the measure of the arc, not the length of the arc. If you need to look back in the previous section for arc length versus arc measure, go ahead and do that. But this is the measure of the arc. So the measure of arc FE is 53 degrees. And we're supposed to find the measure of arc DE. Well, my theorem just told me that as long as the diameter is perpendicular to the chord, then this arc, the whole arc FD, has been bisected. So if this part FE is 53, well, then the other part, ED, is also 53 degrees. And DE and ED are, of course, the same thing. So the measure of DE, that arc with the curve on top, is equal to 53 degrees. Now they want us to find the measure of arc DB. Well, I know that the whole arc EDB, would be a semicircle, 180 degrees. And now I'm just going to sort of cut out part ED. So I'm going to subtract away that 53, and that would leave me with dB. So 180 minus 53 equals 127 degrees, and that's the measure of arc dB. Very nice. Now these next three parts rather, are about the length of some of the segments. So we've talked now about bisecting the arc, now we want to talk about bisecting the segments. So they say that FD is 16, and then we're supposed to find DG. Well, if the chord got bisected, then it's just half of that. Let's get a new color for the segments portion here. So DG is 1/2 of 16, which is 8. And we were talking about centimeters, so this is 8 centimeters. Now AG and GE is a little bit trickier. Notice that AG and GE together form a radius which would be 10. So I know that this whole thing here is 10. So I know if I can find just part of it, then I'll be able to find the other part with subtraction. So I'm going to call this part AGX, and then I just found out that GD is 8. And now a little trick that you'll see here often in this section is that you actually have to draw in an extra radius. So I'm going to draw in the radius from A to D. And because that's a radius, I know that it's 10 centimeters. And now I have a right triangle where I know the hypotenuse and one of the legs, and I need the other leg. So the easiest thing to do there is just going to be the Pythagorean theorem. So we'll say x squared plus 8 squared is equal to 10 squared. When you solve that, x squared plus 64 is equal to 100. And then x squared is equal to 100 minus 64 is 36. And so the square root then, x is equal to 6, square rooted. Now you might have noticed that this was actually a 3, 4, 5 triangle multiplied by 2. 3 times 2 is 6, 4 times 2 is 8, 5 times 2 is 10. So you could have sort of gotten that answer of 6 without much additional work. But the Pythagorean theorem will always work. Just depends whether or not you've memorized your Pythagorean triples. So then x was AG, so AG is 6. So that means GE, the leftover part, GE is 10 minus 6, which is 4 centimeters. All right. So that's our second theorem, and now we're going to look at just one more theorem and an example that goes with that. All right. Theorem 10.4. In a circle or in congruent circles, two chords are congruent if and only if they are equidistant from the center. So a couple things to notice about this. One is we've got our if and only if phrase here again. So that means we could say two chords are congruent if they are equidistant from the center, or we could say if two chords are equidistant from the center, then they are congruent. We can flip the hypothesis and the conclusion there, making what we call the converse. All right, so let's use this theorem in this problem here. So it says chords Ki and NL are equidistant, meaning the same distance from point H. If the radius of circle H is 15 and Ki is equal to 24, find Hj and NL. Well, they've told us that they're equidistant, meaning the distance is equal. So Hj must be congruent to Hm, those distances. And our theorem just said two chords are congruent if and only if they are equidistant from the center. So that means that Ki must be congruent to NL. So if Ki is 24, then NL is 24. So NL equals 24. I know that we're talking about the line segments, the chords, not the arcs, because we didn't put the bar over, or I'm sorry, because we did put the bar over them and not that little curve for the arc. So now we know that NL is 24, and now we also need to find HJ. So HJ is sort of this little piece here, so let's call this X. And what we're going to do again is just like in the last problem, we're going to draw in a radius and make a right triangle. When we measure the distance, we know that in order to measure the distance, we created right angles here. So we have a perpendicular line, a right angle there. So I'm going to draw in my radius. The radius I know is 15. And the leg here is 12. I get the 12 by cutting 24 in half, because from the last theorem, I know that if my radius is perpendicular to my chord, it bisects it. So if the whole chord was 24, I bisected it with this perpendicular radius here, bisected the chord with my perpendicular radius, then I took the 24, cut it in half to get 12. And hey, look at that, we've got another right triangle where we know the hypotenuse and the leg. So that means we're going to use some Pythagorean theorem. So x squared plus 12 squared equals 15 squared. And if you work that out, we know that 12 squared is 144. 15 squared is 225. When we subtract, we're going to get x squared is equal to 81. Square root both sides to get the x alone. And x equals 9. You could again have noticed that this was actually a 3, 4, 5 Pythagorean triple. But if you don't have those memorized, that's okay. Pythagorean theorem does the trick. So we've noticed here that drawing this extra radius in and making a right triangle can be very helpful in these problems. Also, you might need to use more than one theorem in each problem. In this case, we use theorem 10.4 and 10.3. We had to remember that we cut this in half because of the perpendicular there. And anytime, they don't say it specifically, but when they talk about things being equidistant, you've got to measure with the perpendicular. You wouldn't measure the distance from this line Ki to the point H without being perpendicular. So there we go. There are our theorems for section 10.3.